All right, so now that we're starting to think of definite integrals in terms of area, we can actually go back to some of our properties of definite integrals. We've seen these before, but let's now revisit them with this idea of area. So let's suppose we're going to integrate a function f of x from a to a, where the upper limit and the lower limit here are equal to each other. We had this property that if the upper limit and the lower limit were equal to each other, well, then the definite integral is 0. Well, now we're starting to think of what we're doing is we're calculating the area under the graph extending from x equals a to x equals a. So really what we're doing here is this definite integral, it's almost like calculating the area of a rectangle or a region with 0 width. So we're saying that the area of a rectangle with 0 width has 0 area. So that's kind of a key thing here. The limits of integration, if we go back to any of these previous examples, so say like this circle one we looked at, if we're integrating from 0 to 2, well, that's kind of describing like the width of our region in some way. And all these other ones. When we looked at this one, from 0 to 2, that was describing like the width of our region. And so the limits of integration really describe the width of our region. So if we're starting at A and we're integrating till A, we haven't gone anywhere. It's the same starting and ending point, so our width is 0. So the area of a rectangle, or really a region with 0 width, well, the area is 0. So that's what this definite integral property says. Now we also looked at this other definite integral property, and this was where we could split up the integral into two separate integrals, or if we think of it a different way, we can, if we have two separate integrals and the limits of integration sort of match up in some way, so here we're integrating from a to m, and then here we're integrating from m to b, if those limits of integration match up, we can consolidate them into one definite integral. So now it's this property is going to make a whole bunch more sense now if we think of it in terms of area. So as a little example, let's suppose that we have this function f of x, and we were interested in integrating from, we'll say here, x equals a to x equals b. And let's suppose that instead of integrating directly from a to b, we kind of stopped off at some point in the middle. So let's suppose that we stopped off at this point m in the middle. And what we can do is we can think about this area on the left from a to m. We can think about this area from m to b. And that's really what these two integrals are calculating. This integral from here is really describing the area under the curve from a to m. And this integral here is really describing the integral under, or the area under the curve from m to b. And if we have these two distinct regions that match up right next to each other, They're right next to each other here. So we have this one region that goes from A to M, and then we have this other region that goes from M to B, and they kind of match up right at x equals M here. Well, we can just add this area to this area, and we should get the area that goes from A all the way to B. So this breaking point in the middle, this kind of little pause point in the middle, really doesn't affect the area calculation. That's what this is saying. So another way to think of it, it's the area on the left plus the area on the right is just equal to the entire area. That's a fun property now that hopefully makes a little bit more sense in the context of areas under the curve. All right. So in the next little section, we're going to be talking about more properties of definite integrals, but now in regard to special types of functions. So we'll look at that next, and then once we're finished with that, I'll do it for this lesson. So we'll see you there.